All right, good morning. Oh no, it's good afternoon. Good afternoon. Welcome to 1038's lovely mall space. And this afternoon we are going to talk about pneumatics, specifically pneumatics for FRC teams. So we will, and I'm Paul George, for those of you that need it when I do this. Oh, I got to turn it on. You're going to edit that out, right?
Yeah.
There we go. All right, so the agenda, learning objectives. That's the first thing. So what I want from you is to, don't follow me, just leave it alone. Sorry, I should have had this ready to start. As you can tell, this is very informal. I want it to be interactive. I don't want to be the only one talking the whole time. So, learning objectives. I know what I want to present to you. The question is, what do you want? What do you want to learn from today? Because it doesn't do me any good to tell you what I think is important if it doesn't meet what you want. So, who wants to offer up their learning objective? First one. Yes.
I think we'd like to learn, 4279 would like to learn how to get started with pneumatics. We have not used them yet. We don't really have anybody with the background knowledge of pneumatics.
So basically, you want it from the ground up.
Yes.
Okay. This is definitely not an advanced class on pneumatics. This is a beginner's class. Okay. There's a sign-out sheet, folks, that it's going around. If you could grab the sign-up sheet, make sure you sign in. So, okay, ground up, that's good. Who else has a learning objective? Another way to think of it is, after today, I will be able to do what? That's another way to think of a learning objective. He's signing in, he can only do one thing at a time. Vicki, what do you want to learn?
It kind of goes in with getting started, but honestly, I'd like to know the definition, so I actually have some street cred with this.
Okay. You want some definitions. All right? I'm not going to write down street cred, but I've never heard anybody use street cred and pneumatics in the same sentence before, so that is absolutely a first thing. Cool. Okay. How about anybody else? Nick.
Be able to set up pneumatic system without excessive help from Alexander.
Say that again?
Without a lot of help from Alexander.
Okay, so one thing I can tell you, this class is not. We will not talk about programming the CREO in terms. So to answer the question about getting started, right? You must use the CREO as part of the system. It has to control the compressor. That's a requirement of the FRC rules. I do not cover how to program the compressor in this class. That's a separate, or how to wire it to the CREO. Although afterwards, if you want to, we can talk about that real quick. It's actually pretty easy.
What is CREO?
What is CREO? Okay. Hold that thought. I will come back to that later. I will write that down so I do not forget.
Can I give you one more objective?
Yes. Absolutely.
I guess what I'd like to also hear, since you've been around and done this for a while, is how important has pneumatics been to winning strategies? You know, like maybe give some examples of, you know, obviously in this year's competition, it seemed to me from an outsider's viewpoint that it turned out to be pretty important. We didn't use it, but we would have liked to.
Okay? That'll be a very good discussion. Anything else? You guys are all easy. You have any more objectives?
Along the lines of this gentleman said, kind of with the, I guess I'd like the big picture about how are pneumatics used, what are they good for, what are they not good for, that type of thing. And I'd like to know what are the components that go into the pneumatic system.
Okay.
How it all fits together.
Yeah, from a practical standpoint, since you've been involved in many of the games, maybe we can, my only exposure was this last year's game, so it'd be interesting to hear about how they were using some other ones.
Okay, so I added components to the getting started and roundup, so that's included in that, and I put down best use of pneumatics, so that'll be another good discussion. How about the students? Any of you guys want to offer up any learning objectives? They drag me here, I don't want to be here. Where's my iPhone so I can play games? Did you record that?
Maybe kind of like what he said, what are the advantages versus disadvantages of using pneumatics and systems?
Okay, all right. Sure.
So, like, what are the different options? Like, do you need to have the compressor on board or not on board?
Okay, we'll talk about that. Yep. Options. All right. Great. Okay.
And all other words of wisdom we have.
Don't ever catch the first bug. That's the first word of wisdom I have. All right, so I apologize. I normally have everybody introduce themselves at the beginning. So we could start here in the front. If everybody could just introduce themselves. What team you're on?
Yeah, I'm Rob Dubell from 4279. We're kind of a newer group, second year this past season.
My name is Marcus Dubell.
I'm Dave Barringer. I'm from No Team.
Yet? You hoping to start a team?
Hoping that one will appear and I can join it.
Okay.
I'm Nick Mulkey, and I'm from 1038.
I'm Mike Yam from 4028.
I'm Charlie Taylor from 428.
Okay. All right. Well, those are a list of very good learning objectives, and I believe that I'm already prepared to answer these questions, but we'll see. And we will reconnect at the end to make sure that if I have not answered the questions over there or the learning objectives, that we do cover. So, just so happens we will talk about definitions for Big E. We'll go through all the components. We'll also talk about how to make drawings, so no one mentioned that. So, as engineers, scientists, we typically make drawings of systems before we build them. And there are ways to use ANSI symbols to create pneumatic drawings. So we'll actually go through that as well. I'll talk about what's the minimum robot circuit that 2013 rules require. So one caveat about this talk is this is all based on 2013 rules. In 2014, who knows what they will specify, okay? Again, I went back and looked through the 2013 rules were almost exactly the same as 2012. So they don't change pneumatics too much. At least they haven't. But who knows? They could throw it out the window, right? I mean, whoever thought that they would would go with a robot perimeter versus length, length and width, right, for the size of the robot. That was a surprise for me. So anyways, so that's a big caveat. You never know. You have to read the rules. Bottom line is if you're going to use pneumatics, you must read the rules. And one thing, well, we'll get into that too. Okay. We'll actually do a cylinder sizing exercise. We'll talk about air consumption, which is a big deal. And at the end, I'd like to get your feedback on the whole presentation. Any questions? So, like I said, I want to make this nice and informal, and so please ask questions as we go along. Yes.
You introduce yourself,
Oh, I'm sorry.
or did we miss that?
You missed it. I'm Paul George. I'm a 1038, so I wear many hats. For those that don't know, I'm the team leader for 1038. I am the co-chair of the Queen City Planning Committee. I am also an FTA, so I'm the first technical advisor, which means that I go to events and I'm the technical resource to make sure the events run on time, make sure the fields get set up, built properly, make sure that when we're done, it's taken apart and put back in the case and get back on the truck. I also do training for some of the key volunteers first. And I'm also part of the Ohio First initiative that is coming, that we're working on. By the way, if anybody wants to be an officer on Ohio First, there are many slots open if you don't know what that is. Ohio First is a program to help grow, is an organization that we're going to kick off to help grow First Robotics in Ohio. Okay? And with the objective that at some point, well, I think we'll be forced to go into some kind of competition model, district model if you like. And so they will be the people that will be working with First headquarters and writing the documents and implementing the district model. So anyway, anybody has an interest in that, I have contact information. If you're interested in that, just let me know afterwards, and I'll get you into the cycle. So I'm on that. And the last thing, I'm part of the Ohio Advisory Board. No, not the Advisory Board. Operating Committee, Ohio Operating Committee. And that's comprised of the Ohio 2 Buckeye and Queen City Planning Committee chairpersons are on the committee. The FTC partner and the FLL partner are all on that committee. So that's where all the programs come together, and we work together to address issues that are common to all the programs. So, historically, FIRST has not been very good at FLL does their thing, FRC does their thing. The different programs don't talk too much. So this is the beginning of getting the right people together, the leaders of those organizations, to start talking and develop a program that looks like FIRST for everything, right? So, all right, you're welcome. Yes, you had a question. Where can you get a copy of the rules? I did not bring the copy of the rules with me. You have to go to the US First website. You have to go to the US First website, click on FRC, and then it says game information or something like that, competition information, and you can get right to the rules. And you can either browse it on the website, or you can actually download it as a PDF. And actually, there's an app for that. They have an iPhone and a Android. Thank you. I wanted to say archive, and I'm going, that's not right. Android app, and you can actually view the rules on your smartphone. It's a little more cumbersome on your phone, because you kind of have to know where to go, and they have these many subsections. You have to kind of work your way down to the right place. It's a lot harder to find stuff you can't search. That's your question? Yes? Oh, Nick, I thought you had a question. You good? All right. So we'll start off with definitions. And the first thing we'll do is talk about pneumatics. So, here's the definition for pneumatics. Pneumatics is one of the earliest work processes or machines that humans devised, right? So the first thing to devise were water wheels, right? And then what came after that? What came after that? What did people start using after that? Windmills? Yeah, that's sort of like a a waterfall. They use steam, right? They created steam generators. So steam is not technically pneumatics, but if you think about a gas that's under pressure, it's the same concepts. Okay. So, advantages and disadvantages. What do you think of the advantages of pneumatics are? See, I like you guys. I like this interactive thing.
It's fast.
It can be very fast. Yeah. It can be compact. Correct. What else? Yep. Lightweight compared to a. Yeah. You have to be careful about that comparison, but it can be. Okay. What other advantages? If I want to take a motor, use a motor, but I'm doing a linear actuation, what do I have to do? If I have a motor that's rotating, but I really want to do is you need to convert that rotary motion into linear. So what's the nice thing about pneumatics? It's already linear, right? You have, in fact, 99% of the applications for pneumatics are linear. So it has that advantage, is it converting it directly into linear motion.
I guess you could also have rotation.
They do make rotation. They do make air motors, and they do make rotating. In fact, I have one. I have to get it. Cylinders that are rotating cylinders. You can get them from like 90 degrees, 180 degrees. You can get some that are adjustable. The problem with those is that they're relatively expensive. They are used, and they can be very useful. But again, most people go right to electric motor for a robot because you have battery. What else? Anything else for pneumatics? Well, one of the advantages, it's not really robotics related, but I'll tell you anyways. In some industries, you're operating in a hazardous location, okay? And to do electric in a hazardous location takes a lot of extra stuff, precautions, so that you don't create sparks, create an explosion. Pneumatics are inherently safe in that you can't create the sparks. So that's one of the big advantages that they have in industry. All right, what might be some of the disadvantages?
Don't you have to fairly recompress the air?
Recompress the air. I'm not sure what you're trying to say, but you're constantly using up the air, so you have to constantly replenish the air. Correct. So one of the big disadvantages of pneumatics is that you're taking electric energy, using that to convert it into kinetic energy, the air pressure, right? And then doing the air pressure to make work. Versus a battery in a motor, you're doing a direct conversion into motion. So you have some efficiency losses associated with using pneumatics.
As you lose capacity, as you use up capacity in a battery, 12, 0.
Right.
Whereas where if you have a PSI in a cylinder, you got 125, 175, 50, 20. So you have less energy as you're going down, as you're using up your.
Correct.
Once you drop, if you needed 125 to get frisbee, and you used up the 125, now you're down to 100 psi. It's not going to go as far.
Correct. So there is an electric amp analogy as well.
Right.
But what you're saying is very true. Is that you have a reservoir of air, and as you use air out of that container, right, the pressure goes down, which means that if you're depending on it to be at a certain pressure, it may not be available when you go time to actually use it. But we have the same problem with batteries in that if you have too many motors connected to the battery and you
you're trying to draw more current than the battery can deliver, what happens? Well, the voltage goes down, right? So you have the same problem with electric systems. But yeah, it's definitely a problem with pneumatics. The problem with, and when you do that though, what do you have to do? You have to recharge. So the disadvantage is, on the electric side, you just stop using it, and now you've got the current available. On the pneumatic side, you have to recharge, and it takes some period of time to recharge it, and make that pressure available. So that's the big disadvantage. of
Pressure regulator or something like that, you at least
Right.
continue to have the pressure that you were designed for.
So the big thing is pneumatics, you have to design for that fluctuation in pressure. This is the bottom line. Okay. Let's see. Another area of disadvantage is low accuracy. Right. So on a cylinder, we'll get into what a cylinder is. But if you're trying to stop midway, good luck. Right. Basically, you have two positions: all the way extended, all the way retracted, nothing in between. An electric motor, you can put sensors on, and that's where you can stop. You can be very accurate in terms of stopping in a very precise position. Not so with pneumatics. The other thing too is sometimes, not many times, it can be hard to get it to repeat adjustments. Okay, so a lot of the fine tuning you do in pneumatics, it's hard to go back to that setting. Right? So, or if you have two cylinders that you want to extend exactly the same rate, getting the flow controls adjusted to the right, and I'm using terms you guys don't understand. But basically, just assume it's an adjustment. It's hard to get both of them adjusted exactly right. Okay? So with electric, it's much easier. So that's the other problem with pneumatics. Anything else? So here's a couple examples of pneumatic systems. People don't think of it, but a pipe organ is a pneumatic system. You're taking air, you pressurize it, you push it over a vibrating tube, and you create sound. That's a pneumatic system. Remember the old pump organs? That's what you're doing. You're pumping up, creating pressure. That's an old picture of some guy using a jackhammer. That's a pneumatic system. They use gas-powered compressors. So why do you think that they did that? Why did they use compressed air for jackhammer? What do you think? Yeah.
Fast.
It was fast. Why didn't they use electric?
Electric wasn't as powerful as air.
Okay. At the time, especially like probably when that picture was taken, electric motors were not we didn't have superconducting magnets, right? The high capacity magnets. So the motors were very large. So you didn't want that motor on the jackhammer. So as far as the user was concerned, having just an air line coming to it, that was the best solution at the time. Today, what do they have? They have electric jackhammers that work almost as good as those. So. All right. So Vicki, do you know what pneumatics means now? What it is? What does it mean?
Pressurized air creates a
Okay. Very good. So pressure, what is pressure? What is pressure? Well, there it is. It's defined right there. Come on. Is there only one kind of pressure? Yeah, what? Yes, Nick.
You have it written up there. If pressure is the measure of potential energy stored in
Right.
volume.
That's why I said it's up there. I'm not going to read it. So is there only one kind of pressure? How do I measure pressure? What's that? Pounds per square inch. Very good. And there is the conversion into, I can use my pointer. There's a conversion into Newton per meter squared, or pascals if you guys are into CSI. CSI? No, what's the SI units? SI. CSI, that's
That's a TV show.
TV show. All right. I've always done it in English units. So So, but when you're measuring pressure, it's all relative to something, okay? And there's two things, gauge pressure and absolute pressure. So, here's a pressure gauge. What do you think it measures? Absolute or relative? Gauge pressure. Well, yeah, that's where the name came from, right? But it's measuring the difference between the pressure in this tube and atmospheric pressure. Right, so if I make a little sketch. So if this is vacuum, so 0 psi absolute. If I'm measuring gauge pressure, am I measuring to vacuum? What am I measuring against? What is all around us right now? Atmospheric pressure, right? What is atmospheric pressure? 14.7 psi approximately, right? So gauge pressure is this. This is gauge. It's between here and here. Okay? And absolute is measuring this same value here. Let's say it's 100. That's 100 psi gauge. What is it in absolute? This is 14.7. So this is from here to here. So what? 114.7, right? Is there any questions about that? So every gauge should be marked. If it's not marked, you have to assume that it's gauge pressure. If it says, like this one says PSI, that's all it says at the bottom. If it's absolute pressure, it will say PSI-A for absolute, right? So if you get a gauge and you put it in, you're not getting the pressure you think. Make sure you check the units on there to make sure you're getting the right, you get the right gauge. All right. Working pressure. And working pressure is the pressure in your system that you normally, it's normally pressurized to, okay? Normal operating conditions. So if my system is open to atmosphere, is that a normal operating condition? If I'm trying to create pressure in a system, and I have it open to atmosphere, that's not going to work, right? I have to have a closed system to actually generate pressure, right? Otherwise, it's just going to equalize out the atmosphere. Okay. So why is, well, let me see. This is important because all devices, or almost all devices, will have a nominal working pressure, maximum nominal working pressure, okay? This one is rated 160 psi. I don't know what the nominal working pressure is. I'm guessing 160 psi. I don't have the specs, okay? So if your system can generate 200 psi, can you put this gauge in that system? Well, yeah, sure you can. You're just going to blow the face off. So you're going to waste some money. But yeah, the thing is, you need to make sure that the maximum operating pressure or working pressure of the devices you use is less than the maximum pressure you can have in your system. And FRC specifies that. They specify that the pressure outside the compressor, which is creating your pressure, has to be rated at least 125 psi. Okay? So anything you put in the high pressure side has to be, so connected to the side where the compressor is, has to be rated for 125 psi or more. That's one of their requirements.
Rated as by the manufacturer?
Rated by the manufacturer, right.
You cannot manufacture your own?
You cannot manufacture your own pneumatic components.
Okay.
So you must use commercial off-the-shelf pneumatic components. Now, there are some exclusions to that. So, for example, vacuum technically is a pneumatic system, but is excluded from the pneumatic requirements. So, if you put a vacuum generator on your machine and you use that vacuum then, like to pick up the frisbee or whatever it is, that does not have to follow the requirements of the pneumatics rules. Okay. But if you're going to attach anything on the high pressure port of your compressor, then it must be a COTS and it must be rated by the manufacturer at least 125 PSI working pressure. So what people do is, for safety reasons, so this is rated 160 PSI, or it'll measure up to 160 PSI, but it probably can withstand like 200 PSI before it ruptures, right? Because everybody, they always put a safety factor in there. You wouldn't want this to be rated at only 161 PSI, right? Because there's a good chance it might get overpressurized and then you've ruined it. So they usually specify a working pressure and a burst pressure typically. Yes?
What do they specify as a maximum pressure? I think that there would be some element there as well.
In terms of what FIRST requires in the rules, they do not have a requirement for the burst pressure, because they know that the burst pressure is always going to be above what the working pressure is. So they know if you have a device that's rated to work up to 125 PSI, its burst pressure will be above that and you'll have a safe system.
So you can't have a pump that'll go to 200, you can't pressurize
I
your...
think his question was, with, and I read it in
Yeah.
ahead, there's a 125 PSI maximum
Oh, in the system.
But there's a
Right.
125 PSI relief valve.
Okay.
That's required, so if nothing will go.
Got it, okay,
Great. So this is a compressor.
right.
Actually has two outlet ports. This is an old style compressor. We don't use these anymore. So we would connect the rest of our system to one side. On this side is a rupture disc pressure relief valve set at 125 PSI. So the other thing too is that, you were asking this earlier, you must use a FRC specific compressor to charge your system. So whether it's on the robot or off the robot, you must use that to charge your system. So one of the things that's been happening, where did it go? I have to go get one. People have been using the white air tanks because they're lightweight. Used to be, there was a time that they restricted it to 2 or 3. But because of weight, because they were made out of steel, people couldn't use, when they made them unrestricted, you couldn't use a whole lot of them because they weigh a ton. But when they came out with these plastic ones, people were putting lots and lots on them. And they were having problems because one team told me at one event it takes them 17 minutes to fill up all their air tanks. Because they had, I don't know how many they had on there. They had like 20, they had like 20 air tanks on there. It took them like 17 minutes. So, so you have to be conscious of that, okay? But
So you have, the only mechanism for pressurizing is the FRC.
an FRC approved
compressor.
compressor.
You can't have like a pressurized tank like that.
You
No.
said, yeah, you get a big tank, and you have that back in the pits.
Fill them all up.
Well, what people were doing was they were using the portable electric compressors people use in their garages, you know,
Right,
for
right.
woodworking and stuff, and that's illegal. You cannot connect that to the robot. You cannot pressurize your system with that, okay? You must use one of these. Now, what, I don't know if
Use one-
anybody,
you use one of those to fill up the.
Yeah,
the
I
tank.
don't know, that's a
And
good,
then
that's
use-
a good
and
question.
if the
What's the
tank is
question?
rated at more than 125.
The question was, I have to use this compressor. If I put a, let's say, 20-gallon air receiver, okay, use this compressor to fill up the air receiver. Can I then use the air receiver to charge my robot?
Right.
I don't know, that's a gray area in the rules. All it says is that you must use this compressor, whether it's on board or off board.
Sounds like a black and white area.
Okay,
Was this season the first season that they had the plastic?
no, they had them 2 years ago because we have them on Alley-oop, so. So this robot was around 2012, and we've got 3 air plastic air receivers on the side. Last year we had 8. Oh, well, here, we even had them back, this was Logo Motion. We had plastic ones back then, so that was 2009, right? Is that right? No, that was 2011. 2011, so it's been 3 years now we've been able to use those. Any more questions about pressure at this point? We're going to have more discussions about pressure as we go. So. All right, airflow. Nothing happens in a pneumatic system without air, molecules, air, flowing from one place in the system to the other place in the system. And the way you measure that is in cubic feet per minute. Everybody calls it CFM. And basically it's flow velocity times area. So what's the problem with measuring CFM? What's the equation that determines pressure in a compressible fluid? It's on your hand out there. Temperature. So if I have the exact same amount of molecules, right, and the exact same volume, and I change the temperature, and I raise the temperature, what happens? I raise the temperature, what happens? Look at the formula. If I raise the temperature, flip this around. If I raise the temperature, this is constant, everything else is constant. Make this equal, what has to happen? Pressure has to go up. Pressure has to go up, right? So if my temperature goes up, if this is a constant, the only way that I can counteract that is the pressure has to go up as well. So to accurately measure CFM, you actually know the volume of air that's flowing. You actually have to know the temperature of the system, and it varies. So what people started doing was they said, well, let's set a standard. Let's call it standard cubic feet per minute. Unfortunately, there's no one standard. No one could agree on the standard. There are dozens. Basically, you have to decide what standard you want to use, and then define the temperature and pressure that you're going to use, and then you can measure the cubic feet per minute. I have written down that NIST is fairly common. They use 68 degrees Fahrenheit and 14.696 PSI. When I was working at P&G, and we used pneumatics a lot, we used 70 degrees Fahrenheit and 14.7 PSI to calculate standard cubic feet per minute. That was what my advisor or cohort, who was an expert in pneumatics, said we should use. So that's what we use. And the last terminology term that you want to know is called CV, flow coefficient or flow capacity. And this is a requirement of FRC that any valve, control valve, has a CV of 0.32 or less. So what CV does is limit how much air you can get through a port at any instant in time. That's what it's a measure of. So if I have a CV of 0.32 versus a CV of 6, the one with 6 has, 20 times more capacity for airflow, right? So that allows you to compare valves from two different manufacturers. They both have a CV of 0.32. You know you're going to get the same flow rate through those valves. Yes?
So when it says 0.32, what's the units there?
It is a unitless
Okay.
number. Unitless number.
Is there some special unit for the flow, or
For flow,
yeah, is there a special unit that would be, or
cubic feet per minute? Which one are you talking about?
the 0.32?
The 0.32 is a unitless number. It is the way you calculate it now. There's the calculation right there. But when you do the calculations, all the terms cancel out, and it's unitless. And it was intended to be that way. So that's something that you have to pay attention to, because they don't specify what pneumatic valves that you have to use. All they specify is this. And last year I talked about they only made a few changes to the pneumatic rules. One of the changes they made, I didn't write it down, I apologize, is that the ports have to be on the valve no bigger than 1/8 inch. So, small stuff.
So can you have a port? The port's going to regulate bath time, right?
The what?
So a port, the size of the port is going to regulate your flow.
Right.
So,
I don't know, the two things together don't make any sense to me,
Okay.
because usually, the size of the hole
Yeah.
is gonna limit how many molecules of air you can get through there, right?
right.
And that's what the CV tells you, basically. So if you have a CV, so I don't know why, but they decided they wanted an 8-inch port. That was in the rules last year. I didn't even know. So,
Okay.
yes.
So when you were talking about the team with the 20-something
Yeah.
cylinders, could they have just had multiple of those pumps? So you can only have one?
You can only have one compressor. That's correct. But that's thinking outside the box. That's a good thought. Nice try, but it doesn't work. So the other thing you do with CV is if you're looking at a cylinder, knowing the CV rating of the solenoid valve allows you to do some calculations, estimation of how fast that cylinder rod will move. I don't have any of those calculations with me, but I know that that's possible because we did it when I was younger, and they had this we had this book, and they had tables, and you looked up in the tables, and it tells you exactly what it is. So I don't have those books anymore. All right, now we've talked about components like crazy. We're going to talk about them in more detail. So this is a compressor up here. I'm just going to lift it up so you can see it. Does everybody see it? This is like I said, an old style compressor. This is an old style compressor. It has 2 ports. These are the discharge ports. This is actually right here, the inlet port. Okay, all it is just a hole with a filter on it, just to keep impurities from coming into the compressor. And I'll ask you guys. I have a little YouTube video queued up that shows how this is a reciprocating piston compressor, how it actually creates pressure. Would you like to see it? Like to see
Yes.
it? All right. Let's see. Hopefully you can hear what it says. Come on.
Fresh?
We need to refresh? Now we're going to watch the advertisement. But at least it's working.
Blue.
One more
You can
second.
skip it now.
It's our dreams live, where visions of tomorrow thrive. And for those who dare to live in this space, those who believe they're destined to do something, to make something.
We need to get that advertisements for first on there.
A reciprocating compressor compresses refrigerant vapor in a cylinder using a piston. In a way, reciprocating compressors are like automobile engines. The pistons are directly driven through a wrist pin and connecting rod from a crankshaft. Depending on their size, reciprocating compressors may have 1 or more cylinders. Multiple cylinders may be arranged in line, opposed, or in a V. In each cylinder, reciprocating compressors have both a suction valve and a discharge valve. These valves give the compressor its ability to pump refrigerant vapor against a pressure difference. They are usually located in the head of the cylinder, in passages connected to the high or low pressure side of the system. Let's follow the compression process in a single-cylinder reciprocating compressor during one complete revolution of the crankshaft. Starting with the piston at the top of its stroke, or at top dead center, the piston begins to move downward as the crankshaft rotates. Because both valves are closed, the downward moving piston reduces the pressure in the cylinder. As the pressure in the cylinder falls below the low side pressure in the suction line, the pressure difference opens the suction valve, letting refrigerant vapor flow into the cylinder. The piston continues down and pulls in more vapor until the cylinder is filled with low-pressure vapor at the bottom of its stroke. Once past bottom dead center, the piston begins its upward stroke. The suction valve closes. As the piston moves up, it reduces the volume of the space in the cylinder, increasing the pressure of the vapor. When the pressure in the cylinder exceeds the high side pressure in the discharge line, the pressure difference pushes the discharge valve open, letting the compressed vapor flow out of the cylinder. This continues until the piston reaches the top of its stroke and most of the compressed vapor has been expelled into the discharge line. When the piston begins its downward stroke, the discharge valve closes. The complete cycle then repeats during each revolution of the crankshaft. This is the mechanical positive displacement vapor compression cycle using a reciprocating compressor. Please take a moment to complete the following learning activity. To continue, make your selection.
Really just pretty easy, huh? So, what was were they talking about air, or what were they talking about?
Freon.
They were talking about a compressor in your air conditioning system, but it's the same, yeah, it's or refrigerator, but it's the same concept. It's not any different. So you got a question?
So would another advantage of having multiple pistons be like a constant flow of air?
Yes. So you can have those pistons. So here, the problem is that you get airs and pulses, right?
Yeah.
And if you have multiple cylinders, you could have them opposed so that when this one is drawing in, this one is discharging air. So they're better able to maintain airflow in your system. So yeah, that's the advantage of having two pistons or more in your system. They also make a thing called a scroll compressor, and it's basically, you can look it up online. Just do Google or on YouTube. There's videos about YouTube about it. Basically, you have two circular scrolls, okay, and they're intertwined, and the gap between them decreases as you go together at the end. So it takes in air up here in a big volume, and then squeezes it down to a small volume, and then but they're continuous chambers rather than one chamber. So you have a continuous flow of air coming out of it. Any other questions about how the compressor works? Okay. So what kind of compressor do you think this is? Is this reciprocating? How many pistons do you think it has? No, look at it. What do you think? One, right? There's only one. If there was two, there'd be another one of these heads. Okay. All right.
So how long is the stroke on that?
I don't know, to tell you the truth. This particular one I've never taken apart, so I don't really know. Oh, I think I closed my presentation. That's the problem with not having, I don't think I can do a go-to slide. Nope. Here?
Next one, right here.
Well, that just goes to the next slide. I don't have actually PowerPoint on this laptop, I just have the player, so. Okay, so that's the compressor. So the requirements, first requirements for the compressor is 1.05 CFM flow rate. Okay, so the manufacturer has to specify the maximum flow rate of the compressor you can use at 1.05. And the maximum working pressure, 120 PSI. Okay, so what that means in a compressor is that I can only put out maximum 120 PSI. Otherwise it starts to bypass. All right? So a high pressure side can, the maximum high pressure side of the system can be is 120 PSI. Now, you cannot use that to do any work directly, and I'll show you that in a minute. Any questions about the compressor? How do you control the compressor? All right, well, we'll talk about that in a minute. Next thing, cylinders. Here's a cylinder. Got a couple fittings on it already. Looks like it's 1/2 inch bore maybe. Maybe what, 5 or 6 inch stroke. So the stroke is how far the rod can extend. And the bore is the internal diameter of this tube. So, whoops. So here's an exploded view, right? Inside, here's your rod. This is the rod that extends out, and there's a piston, what they call a piston, on the very end of it, right? And so the way it works is I add air on this side, I pressurize this side, and I have to exhaust this side, and then it forces the piston forward and in consequence also the rod. So that's how it moves forward. And then to return it back, to retract it, I have to exhaust this side, and I have to apply pressure to this side, and then it will move backward. Now, what happens if I have pressure on both sides of the cylinder, or the piston, in both ports? If I have pressure here and I have pressure here, what will happen? Yes?
Whichever will go in the direction of, well, if they're equal pressure implied, then it probably won't move.
Correct, it won't move.
But if one's more powerful, then it'll move more slowly, but it'll move
In the direction of the, right, until what happens?
until it fully extends.
Well, one of two things will happen. One, either it'll fully get to the end of its stroke, or what else could happen?
Or the more powerful one
So depending on how the pressure is created,
So it's
okay,
like a tank it goes.
the high pressure one could equalize to the pressure of the other one, then it'll stop moving. So if the pressures are exactly the same, it'll stop moving. Now there's one catch in that. This is the piston, and the rod is connected to the piston. So what is the equation for force? Mass times acceleration, but that's not quite the one I want. If I want to calculate how much force I can create on the end of this rod, how would I do that? What is the units for pressure? Pounds per square inch. Okay, so pounds force divided by square inches, right? So what do I have here? I have an area, right? So if I take my PSI, 100 PSI, divided by 10 square inches, let's say, then I can create 10 pounds of force, right? What do you notice on this side of the piston? It's less, right? So can I generate as much force in retracting the cylinder as I can going forward? No. That's correct. And the smaller the piston, the bigger the difference, right? It all depends on your rod size and your piston and your bore size. But typically it's worse in smaller pistons than it is in large ones, because you have a large piston, but your bore or your rod size doesn't grow proportionally necessarily, right? So it doesn't take up as much. But anyways, it's something you have to be aware of, right? There are times when it does make a difference. Now, I also have up here single acting and double acting. What kind of cylinder do you think this is? Is it a single acting or double acting?
That would be double.
Double acting, that's correct. What would be a single acting?
If you only have one port, put a vacuum on it, and suck it back into position.
Right, so single acting means you'd only have one port, but you wouldn't use a vacuum. Actually, what they do is they put a spring in here, usually on the rod side, between here and here. So you pressurize the back side of the piston to extend it, and then when you release that pressure, then the spring returns it back to the returns. So that's single acting. All right, What's the other thing that is a problem with cylinders? One last thing you have to be aware of. Well, two more things. Let's do two. Any ideas? No ideas? All right. So, where are my bearing surfaces? What is, you know, I have a rod in here, right? Okay. If I apply force, if I'm holding this stiff and I apply force here, what is resisting that force in the piston, in the cylinder?
Washing down your O-rings.
Correct, right? So you have a bearing right here. Usually this one, in this case, is a centered bronze bushing right here. So you have a bronze bushing, and that's what this one has. So some of that force is here, and the other part of the force is back here on your piston, on your O-rings. So do you think this is designed to take a lot of side force? Side force, this way. It's called side force. No. Right. So that's what you have to be careful of. They're all designed to apply the force. I don't know what's that right. What's the right word? Tangent is not normal. It's normal. Yeah. Apply the force normally. Okay. Now they can take a certain amount of side force. So for example, in our robot, alley-oop robot, we had one. It was vertically in the robot, like this. And then we extended it for the alley-oop game. They had 4-inch barriers between the bridges. And so to go over that bridge, our robot wouldn't do it normally. So we had to do a wheelie on the front wheels. So we used 2 cylinders, one on each side, pop the wheelie, and then, but when we did that, what was level here now is like this. Okay? But it's just a relatively small amount of side load. It wasn't possible. But it is possible if you put too much side loading on here to ruin. In industry, what happens is you end up ruining the seals, and then it starts leaking, and then you lose some force. For robotics, typically what happens is you bend the line. And we've done that many times.
For this year's game, this last season, did you use both single acting and double acting on that robot?
All of ours are double acting.
Okay.
We rarely ever use single acting. For one, all the cylinders we have in the back are double acting, but you can order single acting. So one of the things in terms of what's available, like Bimba last year, I think you could order 3 free cylinders. Whether or not that was, single acting was available, I don't know. But there are definitely advantages to have a single acting, right, where you want to do something at the very end, that guarantee it goes in one direction, rather than, or ensure that it stays that direction, right? So you drop, nice thing about single acting, let's say you want this to be retracted when power on your robot goes off. So if you have air, your air could still be on, you still have air in your system, but you can have a leak, right? And the leak goes away. But if you have a spring return, then you can make sure it's always in that position of the air. So, but we've never had an occasion, as far as I know. And you can put the spring externally too, but it has to overcome the air pressure. So side loading, and the other thing too is when you're calculating force, right? If I'm doing normal, then I have the 100% of the force available. If I'm doing an angle, then I have less force than, right, based on the angle that's it. All right. Any more questions about cylinders? Next thing, solenoid valves. Please ignore the switch here. So this is a solenoid valve. This one actually is illegal. Why? What did I say earlier about CV rating? And then what was the second thing? CV rating of 0.32 and port size. These are 1/4-inch ports. So this valve is not legal anymore. It used to be. That's why we have it. The way you specify a solenoid valve is how many positions you want. So in this case, this has 2 positions, A and B. How many ports? How many ports do you see up there? How many ports? Here's the drawing. How many ports? 1, 2, 3, 4, 5. So this is a 5-ported valve. That's what this is, 5 ports. So pressure in. This is my pressure in. This is in one position I get pressure out. In the other position I get pressure out. So when I have pressure here, I need the exhaust. Remember on the cylinder, I need to exhaust the other side of the cylinder. Right? So what happens is when this has pressure, this side, this is exhausting this side. So this is pressure, this is exhaust. And you can see that up here, right? So, well, it's not obvious from here. But that's what that's what that does. Okay, I'm confusing myself. So then when you reverse it, this side will be pressurized, and this one will be exhausted to air. So, and they're marked so that you know. So there's A and B. This is marked pressure, P for pressure. And then this is R1 and R2. So R1 goes to A and R2 goes to B. Usually they're marked RA and RB. It's usually what they are. Now, this solenoid valve has 2 what? Actuators, right? And they're both electric. So to make this one work, how does this work? When I put voltage on this side, this solenoid, then the piston inside port moves to the right. When I apply voltage on this side, then it moves back the other way. So again, just like in the cylinder, if I have voltage on both of these, what happens? What? It doesn't move, right. So you have to make this work, you have to turn off voltage on this side and turn on voltage on that side. Now some solenoid valves have detents into the actuator. You can combine with detents so that once you move it in one direction, it stays there.
What's it,
A detent, yeah, we'll call it a detent. I don't know why. So it will move in that. So to get away from the problem of having voltage on both sides, you turn it on, make sure it moves, and then you turn the power off. So the next time you turn power on, you know there's no power on both sides. Okay. By default, unless there is a spring in here to do return to the other side, what you can do is you can add a spring to one side to force it to one side. That's the other thing you can do. This one is a single acting instead of double. So instead of having 2 solenoid valves, this one only has 1. And then there's a spring, and I think the spring is in here. So you energize this, pushes it in one direction, and then when you take power off of here, then the spring pulls it back the other direction. And just about every solenoid valve has some way to override the signal or to cause this. So as long as you have power off on here, you can push this button and it will cause it to actuate, so switch to the other side. Now, this one requires air to do that. So it's a little complicated, but some solenoid valves are direct acting. In other words, the solenoid in here operates directly on the spool to move it over. And this one is air assisted. So actually this has another spool in it that they use pressure from this port to actually use that to move the spool. So even if you have electric on here, if you don't have any air on there, this will not work.
So is the air acting as part of the force to drive that solenoid piston?
Right.
Or
In this
is
case,
it a switch?
No, it's actually, so think of this almost as 2 solenoid valves in one. So there's a mini one in here that's using that air to help assist the move the spool, right? Yeah. But a lot of them are just direct acting, you don't need that. So, and a lot of times you don't even care, right? Because you're going to have air, you're going to have electrical. It's only when you get into situations where shutdowns or inadvertent loss of air or something where you want the system to do something specifically, that you need to pay attention to those things.
But I would think that if you're thinking about sort of your air pressure as a precious commodity here,
Right.
are you going to be using extra, are you going to, I mean, how efficient is it, I guess?
It's really very efficient. The spool in here is very small. And the only thing it does is because you're using air and it's compressible, right?
Right.
It does take a fraction of a second longer for a piloted valve to actuate than it does for one that's directly activated. All right. So this is the ANSI symbol for solenoid valve. And again, it's a 5-port. So these arrows show the direction of air. And so this is in the default location. And then what happens is in reality is these are the air connections between the ports when you're switched to the opposite side. Okay? Next thing, shut-off valve, you must have a way to discharge all the air in your system. So you need to be able to release all the air. And this is a small ball valve that you can use. They make plastic ball valves that you can use. In fact, here's a plastic version. Right here. So that's one of the things you must have. Regulators. So this is how we go from the 120 psi here out of the compressor to the 60 psi that you're allowed to use maximum to control your solenoid. To control your cylinders. So you have to have a regulator, right? It's usually adjustable. You have to set it for 60 psi. You must have a gauge. If you notice on here, there are ports on all sides on a regulator, and the important thing you need to look for is right here is a little. I'll pass this around. There's a little arrow. That arrow indicates the inlet port of that regulator. So you must connect your high pressure side to the inlet port. The other 3 ports are outlets. The one immediately opposite the inlet port is usually the one you connect to the rest of your system. The other 2 are for gauges. So it allows you, the reason there's 2, that way you can orient that regulator any way you want. And pressure relief valve. So that's what's on the.
I'm sorry.
Yeah, go ahead.
Question.
No problem.
So you said that the working relief, or the line that you connect to drive a cylinder should be directly across. I mean, is that for efficiency purposes, or is there a requirement, or is it just what's usually done?
It's just what's usually done. I don't know if usually well. On large regulators, those ports are different sizes. So like on a 3/4 inch regulator, it could be 3/4, 3/4, but the port size might be only 1/4 inch for the gauges. So it's just a efficiency you want to do. Okay. So I just do that as a matter of course. I always do in and out, and then the other 2
Gotcha. Okay.
gauges. Pressure relief valve or ruptured disc. And a ruptured disc actually has a small disc inside there, and it actually breaks, and that's what relieves all the pressure. And so to repair it, you actually have to take it apart, put a new disc in, and then put it back together. Yes?
So what would be the advantage of using that form of pressure relief valve versus the shut-off valve?
Okay.
That's automatic.
This one is automatic. So what it is a safety device in your system. And what it is set for 125 psi, so that if in any case, in any circumstances, the pressure here gets higher than 125 psi, it ruptures automatically and prevents what? Something else from rupturing, right? Catastrophically. Well, the thing here with this rupture disc, it's contained. So even though it ruptures, it's very, very small risk of injury. If something else ruptures, you could have shrapnel and somebody could get injured. So that's why you put a ruptured disc or a pressure relief valve. And usually these pressure relief valves, even though they're usually set for a specific pressure, you can't adjust them. Some you can. Yes. Can you have a ruptured disc? Yes. Yeah. You don't have to. You can have one or the other. You don't have to have both.
They work together.
You don't want to have more than one. You usually just want to have one in your system, and it's usually around the compressor. So we'll talk more about where it goes in the circuit here in a few minutes. So this is the symbol for a ruptured disc, and this one for a pressure relief valve. Pressure switch. You must have a pressure switch. So here's a pressure switch. What happens is it switches at 120 psi, and then changes state again. I believe at 80 psi. Maybe it's 85. I can't remember. And I looked it up on the web. It didn't have it in the spec. It just said it switches at 120 psi. So what do you think we use this for? What do we use this for? The pressure switch. Turn the compressor on and off, right? So this is your hysteresis. So your pressure goes up to 120 psi. You turn your compressor off. When this switches, you have to use your CREO and your LabVIEW program or C++ to monitor this input. Then you turn the output off. It turns off your compressor until this switches again. And once it gets to 120 psi, it won't. Once it drops like 119, it doesn't switch at 119. It stays on until 80. I think it's 85 psi. And then that's your signal. Then to turn your compressor back on. So that allows your compressor to cycle rather than be on all the time.
Is it adjustable?
What's that?
Is it adjustable?
The pressure switch? No, it's not. Some are. You can buy them that are. This one is not. And this is the one that you're required to use.
Okay, so you're required to use the unadjustable.
Correct. That's correct.
So pretty much almost all of these are standardized pieces.
They're standardized pieces, that's correct. And then there's two symbols here for the pressure switch. This one's easier to draw. This is I found online. Pressure gauge, everybody knows what a pressure gauge is. We talked about that. Of course, you need fittings and tubing to connect these things. So when you get something like the regulator, right, there's no fittings on there. So here's a regulator. It has ports. So you have to get a fitting that you have to screw into the side of the regulator or device. And you have to make sure that, right? So first you have to make sure that the threads match on the device with the threads here. And then you want to make sure that the other side matches your tubing size. Okay.
Question.
Yes.
How does that tubing fit to the fittings? Is it like a sleeve?
What these are, you do not have to use these fittings. These are compression fittings. So the way they work is you get a tubing of the right size. You just push it in. It's just a friction fit, and you can feel it when you push it in there. And then when you release it, they have this little release lever here. You have to pull back on the release lever, and then you can pull the tubing out. What you had to use in the past, before these were invented, was a ferrule and a nut. So you would put the nut on, you put the ferrule on, then you put this on, you tighten it all down, and the ferrule would get compressed around the outside of the tubing to prevent an air leak. Okay? The fitting was always reusable, but the ferrule was throwaway. Once you use it, you can never undeform it anymore and use it again. These are much simpler to put together as well. They're a lot faster, but in my opinion, higher propensity for leaks. I would much rather use ferrules and nuts, but this is what we have. This is what just about everybody I know of uses, is these.
find that, you know, if you're connecting, disconnecting, it kind of tears up the end of the tube?
We don't try to, we don't
Yeah,
typically
we only try
do
to do it
that.
once.
Okay, I do not have it on my list of components, but they do have connectors specifically made for quick connects. So they have a male and female piece. So the male kind of looks like this, and it has a bulb on the side, different design. I don't know, I'm not, can't remember exactly. But actually, I got one in the back. I can do it. And then there's a female part that matches up with that. And this has a release ring. So you pull the release ring, and then it snaps in there. So if you're going to be connecting, disconnecting, that's what you choose. You should use one of those devices.
And is the tubing always the same size?
No. The tubing is whatever size this tubing is. I'm going to make you read it. Doesn't say. I don't know what the nominal dimension is of the
But I
tubing.
guess you said all ports are
8 inch.
8 inch.
Right. All ports on the valves are 8 inch.
Okay.
Yeah, this ports on the valves are 8 inch. Well, we'll have to look at that up in the rules.
Okay.
Let me write that down, because nice thing is you can get T's. So this is a T. This is a Y connector. So it's like a T. You get a Y connector. This is a coupling. And then on the end of my, well, we'll talk about that in a little bit. I won't spoil the fun. All right, then receiver air tanks, clipboard cells, one's plastic, it's 500 ml, and the steel one is 16 cubic inches. The last thing is the flow controls. Oops. So, when I'm applying air here, how fast is the cylinder going to move? As fast as it can, right? Is that always a good thing? No. Sometimes you want to have a slower extend or slower retract than the other direction, or you want to control both directions. So you have a thing called flow control, and basically, and this one's built into the fitting. You can get ones that are inline, that are separate. This is built in. So there's a little adjustment on top of here. Basically, what it is, is you have a needle valve inside there that's restricting the amount of air that can flow through there at any given point in time. Then they have a check valve on the other side. The check valve means so that when the air is going the other direction, it's going full force. So you don't want to restrict air in both directions. You want to restrict air only in the forward direction. So if you're trying to restrict, so if I'm trying to restrict this air going in this direction, I want to put that on the forward side, on this side, versus the other way around. Okay?
And how's that different than the regulator?
A regulator is always trying to maintain a specific pressure. So it has a diaphragm in there, and it's looking at the difference of pressure between the inlet and outlet. It's trying to maintain that pressure difference. Okay? Where this is just limited, it's not trying to change the pressure, the final pressure. It's trying to change the amount of time it takes for the air to get from your source into the cylinder. ANSI symbols. So, I have for you a printout. I was going to pass these around. This is from Clipper. They call it their simplified ANSI symbols. And they do a comparison between that and the actual ANSI symbols. And most of the ones that you've seen here are based on the documents here. So there's a couple of websites there that you can get documents. Well, the Clippered one is the one you got right there. I just gave it to you. You can download it as a PDF if you want. And then there's others available. Just do a Google search and you'll find it. All right, so we're going to, I've shown you all the symbols. They were next to each one of those devices as we went through, right? So we'll just do this as a group. We'll start at the source, and typically on pneumatic drawings, it's always been left to right. It's just the way they draw them. So what is this right here? That's the compressor, right? Okay. What is this?
Nope, that's not the solenoid. Pressure regulator. Is it fixed or adjustable? It would be adjustable. Right? Because see this arrow right here? That's showing that it's an adjustable pressure regulator. Now, what's this? Solenoid valve, right? How many ports does it have? 1, 2, 3, 4, 5. 5 ported. How many positions does it have? 1, 2. 2 positions. Okay? Get it? What's the actuator on this side? Spring. What's the actuator on this side? I didn't tell you what it was, but it's in there. In the clipper. Look in the back of the clipper. What? Let me ask you this. Is it, we said it was a solenoid valve. I don't see any solenoids. That's why I'm asking. There are no solenoids on there. There's a spring return, and there's a mechanical plunger. That's what the bottom is. So it's just a valve. It's not a solenoid valve. That was a trick question. And then what's the last thing we have in our circuit? Cylinder. Okay. So, we asked about what is the minimum requirements for 2013 FRC. Here's what you need. You need the compressor. We talked about that. The compressor can be on or off the robot. Either way. However, there's a big caveat. The compressor must be controlled by that robot. So what does that means is that not only do you need a quick fitting for the air, right? You also need a quick disconnect for your power connection. Okay? Why would you want to put the compressor off the robot?
It's big and heavy.
It's big and heavy, saves space. What's the other thing that it does? Let me see. 10 amps. That compressor draws 10 amps. You think that's a significant current draw?
Yeah.
Heck yeah. So, if you're trying to drive and you're trying to power the compressor, you've got competing resources using the battery.
So it has to be controlled by the robot, but it has to be powered by the robot.
It has to be powered by the robot. To control it with the robot, it has to be powered off the robot. So,
so you could charge your system while it's still, pressurize your system while it's still connected to the robot's connected to a power source or no?
You have to use the battery that's on the robot. So here's what teams will do when they do that. They will put in a battery in the robot. Now they have to connect the driver station through the tether to the robot. You have to enable the robot, because unless your robot is enabled, it's not turning on any of your outputs. You enable the robot, it's looking at your pressure switch to see whether or not you have low pressure or not. If it's low pressure, then it turns on the compressor. So you will have you have to use one of two things: a spike or a variable speed, like a Jaguar or a Victor, to control turn the compressor on and off. Okay, so you have to dedicate one input, digital input, and one PWM output for the compressor. So you enable the robot, it says run the compressor runs, system's charged. Now you disconnect the wiring from your robot and you disconnect the air hose from the robot and you're good to go. Well, you have to disable the robot. Yeah. Now, what a lot of teams will do then is they will pull that battery out and put a fresh battery in before their competition. What you gotta hope is what? What are you hoping? No? What are you hoping between the time you charge that system and you start the match? What are you hoping?
You don't have a leak?
You don't have a leak, absolutely. Because if you've got a leak, guess what? You got a problem. Now, it depends on how much reservoir space you have on your robot and how big the leak is, right?
So we still don't know the answer about if you could pressurize, have the compressor on a tank.
That I don't know. And I don't know that I don't know. Well, we can look at the rule, but I don't think there's anything that talks about having a real receiver. It just says you have to use your robot.
It says the compressor has to be off the robot, but it doesn't say what else could be off the robot.
Right.
Now, I guess based on what you just said, based on the fact that your pressure switch is not adjustable, it turns on at say 85. Yes.
Well, it turns on. It switches at 120 to start with.
It switches off. Right?
I don't know if it's off or on. I don't know. But whatever. It changes state at 120 psi. So when it's coming up, the pressure's coming up. It's going past 85. Nothing happens. So it gets to 120. Then it changes state.
Right.
Then the pressure starts. You start using pressure. The pressure starts dropping. At 85 psi, it changes state again.
Yeah. So I think it would be important to make sure that as you go to recharge or repressurize your system, that you bleed off the brush pan remaining pressure so it's down below 85, so that it'll give you a complete pressure.
Correct. Yeah.
Okay.
So the other thing you could do though is you know when the robot gets enabled, and you could force the compressor to come on.
Yeah.
As long as the pressure's not at 120, well, you can't do that because you don't know.
You know that the switch
You're
is
just
on.
jumping every time before you start.
Yeah.
Yeah, and you want to make sure basically you want to make sure it's below 85 psi, so that you make sure that you come up to 120. Because otherwise, if it's like 90 psi, right, and it's been through the cycle, so it's on the way down, right?
Yeah.
It's saying, well, I'm good, don't turn on the compressor, but in fact, what you want to do is you want to charge up, right?
Right.
So, but your software, there's no way to know when that switch, whether it's, first time through up, hit the top, or if it's still coming back down.
So let me ask you, is there electronic gauge? Pressure sensor?
You may use a electronic pressure sensor under the following conditions. One, greater than 125 psi. It has to be a COTS device. And two, it has to be less than 400 ohms. So yeah, if you want to use an analog device and hook it up into your an analog input on your robot and monitor it that way, you're most certainly welcome to do that. By the way, there are some other requirements when you have the robot, the compressor off the robot. It has to do with where the rupture disc is and that sort of thing, and I don't remember the details because we've never done it. But. Okay, you must have the pressure relief valve set at 125 psi. You must have one of those. And that must be hard piped to your compressor. So you cannot use tubing. So for example, I cannot put tubing through this fitting and then put my pressure relief valve out here. This connection for this pressure relief valve must be hard piped. Okay? Again, that's a safety thing in terms of making sure things don't rupture. That the pressure relief valve is the first thing to relieve pressure over 125. Let me ask you a question. If this compressor is rated 120 psi, is there any way to get pressure above 120 psi in my system?
Increase the temperature.
Increase the temperature with one way. Vicki, what do you think? Do you think it's possible if this thing's rated 120 psi to get more than 120 psi in the system? He said temperature, but there's another way too.
That's just the rated volume.
That's just the rated volume. Decrease the volume. Oh, interesting. Right? So if I deadhead this pump, you know what deadhead means? So normally I'm coming from this pump out to the rest of my system, like my air receivers and everything. I have place for air to go. Deadheading means that there's no place for air to go. So I've decreased the volume significantly. I deadhead this pump. What do you think will happen when I try to turn it on? Will the pressure go above 120 psi? Yes, absolutely. So that's why they want this hard piped in there, because you can see 500 psi, 1,000 psi instantaneously. And hard piping will withstand those pressures for a short period of time. Before, you know, this thing will give long before that hard pipe. Tubing like that, especially a long piece of tubing, may not. So that's the whole reason for doing hard piping. You don't ever want to deadhead a compressor. All right. You need a stored pressure gauge. So you need a gauge that is on your high pressure side. They call it the stored pressure side. Okay, it tells you what the pressure is at any given point in time. And you need a pressure switch. Okay, so here I have a. Let me go to the next one. A manual dump valve. So here I have a hard pipe system that is pressure switch, pressure gauge, dump valve. Right? That's what I have right here. My pressure relief valve is on the back, is on my compressor, so I'm good there. I don't need that. So I have a pressure gauge, pressure switch, and my manual dump valve. And then, so what is this? So this is my, I'll tell you this. This is my connection from the compressor here. What is this connection for? What is this connection for? To the regulator, to the rest of my system, right? Okay. So. And then the last thing you need would be your working pressure regulator. So this would go piped in just like that between there and your working pressure regulator. Set at a maximum of 60 psi. And gauge. So I need a gauge on the downstream side of my pressure regulator. Right? So all I need to do is take this gauge, put it into my gauge port on this regulator, and I'm good to go. Right? So this is all I need for the robot. Compressor, some tubing, this manifold, and then tubing and my regulator, and I'm good.
Well, you need something.
You need something to do? Why would I want to do that?
You need a actuator or something.
But that's all that's required.
Required to have an actuator.
That's all that's required.
Okay.
You're not required to put an actuator on here. You're not required. So, if I do not have any pneumatic cylinders, not any cylinders on the robot, do I need to put all this stuff on the robot? No, you don't. You only need them if you're going to use pneumatics. So if you don't have a cylinder on there, you don't have to use it. So I think I covered a lot of this stuff. So here's where it talks about the pressure switch has to be connected to the digital sidecar, serial monitor switch, operates the relay module, powers the compressor. see what else I got. Here, outputs from multiple valves may be plumbed together. Okay, so this is one that's kind of weird. Outputs from multiple valves may not be plumbed together into the same input on a pneumatic cylinder. I don't know why you would ever want to do that. So what they're saying is if I had two solenoid valves and then on the output side put T's so that two solenoid valves can control the same cylinder, you cannot do that. So it's basically one solenoid valve, one actuator. I have no idea why anybody would think to put two solenoid valves. I don't know. I've never seen it ever. So, all right.
If you wanted to regulate change the speed of your cylinder, and you get two pressurized pressurized tanks.
Right.
And you had each tank driven by a separate solenoid. You turn them both on, you might be able to push that cylinder faster than just having one on.
Yeah.
Your CV goes up because you've got two flows.
Right. You're still going to be limited by the CV of the valve.
Okay.
Yeah, but there are two of them.
Yeah, the
Right.
CV,
That's what it is. Yeah, exactly. So maybe. But the other thing too is it's going to be a weird circuit anyways because if one is higher and one's lower, if you don't have this one blocked, then that's going to try and get blow pressure into the lower pressure system.
So do you have like water plumbing? You have
Yes, they do have.
backflow valve or
They do
something?
have backflow valves. Yeah, check valves. So we talked about that in that flow control valve, right? It's got a check valve.
Right. Okay.
They do. You can buy check valves. Sure.
I can just use one.
Okay, so real quick, we just talked about all the devices. So here's all the devices in the minimum FRC circuit. So there's your minimum requirements. It's sufficient, by definition, yes. Useful, no, because you can't do any work with it. So what do we need? We need a solenoid valve, and we need some kind of actuator. Now, would you be happy with this circuit? Are you happy with this circuit? You're not happy with that circuit? Are you happy with the circuit? You don't know. It's a leading question, loaded question. Are you happy with the circuit?
No.
Why not?
I don't know.
Well, let me put it this way. Let me ask you this question. Do you care if the compressor is running all the time or not? Or almost all the time? Every time that I actuate this cylinder, what's going to happen? The pressure's going to drop, and it'll probably drop below 85 psi, and the compressor's going to come back right back on. So every time so if I'm cycling this constantly, the compressors are doing what? Running constantly. So now are you happy with that circuit? No. So what do we have to do to fix it? Put a tank in. Absolutely. So you need an air tank to supplement what the compressor supplies, so the compressor is not running as often. Now I can say, let's see, I think it was an alley-oop. We actually could see the robot slow down when the compressor was running. So you'd be going along,
So do you typically build your robots with a compressor on board or no?
We typically build it with onboard because we have not found, and the only time that we don't is when we use the pneumatics to shift the two-speed gear box on the drives. Any other cylinders on there, you cannot store enough air to guarantee you can make a 2-minute and 15-second man.
Gotcha.
So we always put a compressor on. I know there are teams that did it. Probably that team that had 20 air tanks probably did it. Okay? Would I want to be in that situation? No, I would prefer to have a compressor. Because again, if you got a leak on there, right, you're going to be in trouble. Right. The risk for us with the two-speed gearboxes was, okay, so we have a leak, we run out of air, it's like, okay, fine, we'll just run it wherever was the end. It ended up, being the end of the match, we probably won't get it. All right? It's what?
Sometimes it would get stuck in between gears if the air.
Yeah, if it goes too low, if it just happens to be switched when the air went too low, it would get stuck. But the robot would still drive, right? It wouldn't go to neutral. It's not like a neutral position.
No, but it wouldn't drive very.
It wouldn't drive very good that way.
So you used it for more than just the climbing, the pneumatics?
Right. So in Ollie, we used the pneumatics to pull the bridge down.
Yeah.
We had the two kickers that kick us up so we could go over the barrier.
But I meant for this last year.
For this last year, yeah, we had several pneumatic cylinders. So we use them for climbing, like I said. And then, so this mechanism, we lift this up, that's a cylinder, a simple cylinder and cylinder. We also have this cylinder here, which is our prevents the frisbees from contacting the shooter wheel when we're not ready to shoot. So to shoot, we have to retract this, and then we have a kicker here that kicks the frisbee out from underneath the stack. So and as soon as it contacts the shooter wheel, it goes. And then we had them on the two-speed gearbox as well as the shooter. So, one of the questions you asked was, why use pneumatics? Why do you think we use pneumatics on those, in all of those circumstances?
It's fast, number one.
Fast, that's correct. And once you account for, so one of the things that happened is that we knew to climb the pyramid, we needed pneumatics. So now you've made the investment in the compressor and all the other stuff, the space and all that, right? Okay, so now when I come to a decision about when I need an actuator, I don't have to decide, I've already got pneumatics on the machine, so all I need is a small cylinder. Okay, so it's just a solenoid valve and a little bit of tubing and I'm done, right? Versus if I want to do it with and it's a linear actuation, right? Now I need a motor, I probably need a gearbox. Oh, by the way, now I need to translate that rotary motion into linear motion. I still need a Victor controller, or I need a Jaguar. Okay, so the Victor controller Jaguar is probably comparable to the solenoid valve, so that's a wash. The wiring is probably about the same as the tubing, so that's a wash. So it becomes a question of, is it the first one I'm putting on there, or is it some other? Is it I've already made a decision to put it on there, and what the application is.
So if you put it on for a particular reason, then what you're trying to do is see if you can leverage it for a lot of other reasons.
Then we try and leverage it, correct. And the other thing too is, as you noticed on these two cylinders, they're relatively small. So we were concerned, on this particular robot, we were concerned about the space and how much weight we had.
Can we come over there and see that?
Come over, yeah, no problem. Or I can bring the robot over there. So, we wanted to minimize the amount of weight that we had. Right here. As you can see, it's.
So this is for positioning, is what you're talking
This
about?
is
That's
for,
why
we
you
did
lift
this,
it up?
yeah, we did this for two things. When we went to the feeder station,
Yeah.
we'd lift it up to a certain angle to load the frisbee.
Yeah.
Then we'd go back down, and then we would come back up, and then by going back down, we could go underneath the pyramid. Then we would get to the shooting position, we lift back up, and we go to a higher position, and we can shoot the frisbee.
Okay.
Right? And then at one point in time, this was going to be the starting mechanism for climbing the pyramid. So that actually this part of the climbing mechanism is going to be mounted to the side of this. Okay. That didn't all work out. So anyway, stress. Well, we couldn't get the mechanism designed to work the way we wanted to. It was too complicated what we were trying to do. So anyways.
You've got the shifting of the gears, you've got the climbing, you've got the, being able to lift this up and down. And what was the last one you mentioned?
So we got the two cylinders for shooting. that one for lifting this, the climbing the pyramid, and the two-speed gearbox.
So the shooting just basically is an arm that came out that moved the frisbees forward up to the wheel.
Now this is just an arm. Inside there's a pusher.
Yeah.
So if you look at it from this side. Oh yeah. You're only supposed to be 400. That's the problem. Okay, so we just have a pusher here to put that through. So what that would do is that would just make contact. Once it made contact with that, because it's under compression, and just point it right out. And then this is the other cylinder is right here. And that was a stop, because sometimes when you drop the first frisbee in here, just driving around it would vibrate and would contact the wheel. There it goes. So that was to prevent that from happening. So you can imagine trying to design a motor, right? So now if you want to do this with a motor, what does that mechanism look like? Where's the motor, gearbox, some kind of actuator, things in this space? It would be a lot of space. It's much more difficult to design and implement pneumatic gear. So it was obvious because we already were going to use pneumatics for the lifting mechanism. This is like it's almost like
Now, you were aiming at this one, so
we had, and it's all tore up right now, but we had stops. We have different stops on here. So we have a small cylinder that just extends in and out, and we catch steps on here. So if we wanted to go to the lower position, this would extend out farther and catch the first step.
all right. Because the cylinder that you were saying is not very precise.
Right, so this is how we made it more precise. The problem was with this is that we undersized this. So that's why it broke. Yeah, that's why it broke. The other thing that's nice about this, so the same thing here, you could have used, just like we did on this mechanism here, we have a lead screw here, it's on the motor at the bottom, so down there, and what it does is it raises this tray up and down. Okay? So that's a linear application, right? We could have done the same thing here, but again, we were worried about space. Now, what you don't see is, it looks like there's plenty of space, and there is now because of the winch and all the other stuff that went with the level 3 climbing. When we were originally designing it, we said, no, we need to keep this as small as possible. And the other thing too is it's much easier to pivot, a cylinder because you got a crevice connection on one end, and so it's much easier to do. You gotta watch that, because look, at this point, look at the angle of that cylinder, right? It's not normal at all, right?
Yeah.
It's very far away from normal.
Right.
So the size of that cylinder was driven by this final position, not by this position. Because here, you got the full force, you're pretty much normal, it went right up. But pulling it back was a problem. And so that caused that cylinder to go from, I think it was 1 inch to that 1.5 inches.
That's
Maybe
because
that's
you
2 inches.
needed pressure on the backside to pull it
That's
down.
because we needed
To pull it back over.
pull, and not only that, we're on the rod side of the piston too,
Right,
right?
right.
So you lost that force as well. So yeah, it was a touchy. So you had to be cognizant of it when you did the design. Now, did we do all the calculations? No, because it's hard with all the angles and stuff and the
Yeah.
weight to figure out exactly, and the friction. So one of the things you have to be careful about is friction.
Right.
It can kill you in terms of how much force you need. So what we did is we actually had a smaller cylinder. We put it on there and it didn't work. So the next size up.
Eventually,
After you saw this in performance, the robot and everything, would you still use the pneumatics on all the 4 applications you used it on?
Yes, absolutely. I would not do it differently.
Okay.
I would not do it differently.
for the disadvantage you mentioned earlier, if it either is on or off and you can't go halfway, that was really hard for the aiming because we originally planned for a motor and then we changed it, right?
Right.
So it was hard to get more than just all the way up or all the way.
So, and then to get this much stroke, this putting the cylinder here, to get that much stroke, using the lead screw would have been much more complicated in terms of supporting that lead screw bearing-wise and that sort of thing. So this is really the kind of application that a cylinder is really designed for.
Now these two cylinders for lifting,
Yes.
are they like a two-stage, or do you ever put like two-stage cylinders
We
on?
considered 2 stages, but in this case we decided a single stage was more effective. We did some looking at that for 2-stage here, and we found out that it was easier just to use a single stage cylinder with a bigger bore. That was much less complicated actually.
Okay.
Because here we're doing this vertically, right? So we don't have, other than the robot doing a little bit of swinging, we don't have any side loading.
Right.
But when you put two cylinders side by side, now you got two rods. Now you have to consider, how you're going to attach those and have the bearings in there so everything moves nice and smoothly, right? It's more complicated to do that mechanically than it is with a single cylinder.
Now, do they have cylinders where you have like that rod being, that's what I was thinking of as a two-stage, like
Okay.
the plunger
what?
piece would be one inside the other?
Yeah. You know what? I just realized I told you guys wrong earlier. Single acting versus double acting cylinders. These are all single acting cylinders. The double acting cylinder has the rod coming out on both ends. So it has a rod on both ends. That's what a double acting cylinder is. So I apologize.
Okay.
Yeah, that's what double acting is. So this is all single acting, and then you would just put a spring in there for spring return. That's what they would do.
Yeah, okay.
But double acting means two rods,
either
one
way.
rods on each end.
All right.
And then it would be in one position or the other. Well, and sometimes what you'll see is that double acting attached to another cylinder to create multiple positions.
Okay.
Okay. And if this one comes out, so this would extend and moves this one. This one's all the way. I forget. I'm pretty sure you can. So any more questions about application? It's very application specific. You have to look at how much space you have. Is this the first cylinder I'm putting on there, or is it 6? To decide whether or not cylinder is the right answer. Is it a linear actually? It's rotary. I always usually think of motors. So air motors are terrible. No matter how many tanks you had on there, if you had ammo on there, you would be running that compressor. And my understanding is the new compressors. So there's the new compressor. So it's much smaller in size. It's limited to a 4-minute run before it has to shut off. If it runs for more than 4 minutes, you can actually overheat the compressor during the series. Which my understanding is that they have done that already. But you can see we have hard piping coming out of the one. So this one's different in that it only has a single discharge port versus that one. So we had the hard pipe. Here's the pressure relief valve. Here's our pressure switch, the digital gauge, and then our and then, so this is all our high pressure side. All of the air receivers on the high pressure side. And then here's our working pressure pipe. Now, you notice there's another air pressure regulator. So why do we do that?
Different needs on the robot for how much pressure.
Correct. So I can, so the big cylinders I wanted higher pressure. I don't remember exactly.
Not for the shooting.
But I don't think for these I needed such high pressure, so I wanted to reduce the pressure. So the pressure is force, right? If I don't need all that force, it's just a lot.
Next is on
Now, these are our solenoid valves. So what we chose to do is buy in a manifold style. Right? So what you saw there was a single style. And basically what this is. So this same solenoid valve can be put on a single manifold, or it can put in. So all of these are ported together. Now the output ports are separate, right? But you only have to apply one pressure port. So it makes for a nice compact package versus having individuals scattered all over the floor. Now, what does the tubing do for us? Is the tubing length a problem? Well, it takes up volume. So one of the disadvantages of having the manifold is that the tubing length now, if we're coming all the way up here, is very long. What if speed was critical on this application? If I have to pressurize all that tubing all the way up to here, that's going to delay me. So if I want the fastest operating condition I want, it's possible. I want the solenoid valve as close to the actuator as possible. I want to keep those air lines as short as possible. So it's not a problem on the pressure side because it's always pressurized. I mean, you still have a flow restriction problem because you have a longer to do, but at least it's already pressurized. Where here, one side is always exhausted. Now I have to exhaust it. Now I have to pressurize that side, and the other side, which is pressurized, has to be exhausted. So all that air has to flow out. So that's the disadvantage of a manifold style system. But it does simplify your pneumatic tubing because I just bring one pressure in versus having to run that pressure line, tee it off all the different zones. So that's another thing.
You actually have to have a label now. You ran into that problem.
Great. And then these are the override manual overrides. There's little blue buttons. Okay, any more questions here? Very much. Back to the slides. Oh, okay.
Thank you very much.
Oh, you're welcome.
Might be having to cut out for these while I'm grab my jacket.
He's got to be talking too much.
Yes, he did.
All right, so let's continue. Here you can see the port connections on this solenoid valve. So when you start up this system, pressure is going to be applied to this side of the cylinder and it's going to be retracted, right? And what happens is when you energize this side of the solenoid valve, oops, sorry. So in a solenoid valve, when you draw it up, you always draw it in the default position where, so when there's no power applied, where the ports are connected. So here, this is extended. So pressure here goes to that side, and this side is exhausted. And then when you energize it and move the other direction, then this is exhausted, pressure to this side. So. Cylinder sizing. So we talked about this a little bit already. There's the equation, and when you specify the cylinder, you specify all of these items. Okay. And under accessories, one of the things that you might want to consider is you can purchase switches that'll indicate when your cylinder is at a certain position, like usually in the stroke. Okay. So those are many times are helpful, and that way you know you've actually reached that position. But it's one of those things that you have to think about when you purchase the cylinder.
Yeah, it's built into this.
Right. They usually have a magnetic ring in the piston, and then the switches on the outside pick up that magnet switch. So. You notice that there's nothing up there about speed. specifying a cylinder. It will go as fast as the air available will allow it to go, and the mechanism will allow it to go. That's what determines this. Unless you want to slow it down, and you can add flow control, right? You can actually restrict the airflow coming in. So here's an example. You want to lift a 160-pound robot. Why did I say 160 pounds? Well, let's see. So this is for all of you. The limit was 120 pounds for the robot. What did that exclude? Batteries. How much is the battery weight? 14 pounds. What else does it exclude? Nope. The basketballs, but they're ounces. Bumpers. How much does the bumpers weigh? Up to 20 pounds. So that's 34 pounds. So 120 plus 34 is 154. So what did I do? I rounded up to 160. And I wanted to lift the robot 6 inches off the ground. So my stroke was 6 inches. Thanks, guys.
Thank you very much. Appreciate it.
And if you have any more questions as we get through all this, you're more than welcome to come back and talk some more.
Okay,
We'd love to
thank you.
help
Yeah,
you out.
that's
And then I'm sure the video will be posted. You can watch the rest of it too.
Thanks a lot.
You're welcome.
This is about 2 hours into the day.
All right, so minimum 6 inches. Because I want to lift the robot 6 inches, I need a minimum 6-inch stroke. But depending on where that cylinder gets mounted in the robot, right, it's not going to be mounted flat against the ground, right? It's going to have to be up a little bit. So that cylinder was actually like 8 or 9 inches in reality. Okay, so you have to consider that when you're specifying the stroke. It's not just how far you want to move, but where is that cylinder in relation to your mechanism? How are you going to attach it? It might actually be shorter. So if I have to put a coupling in there, right, I might actually have to make it shorter. So. Okay, and then we ended up with a bore based on 50 psi. So why did I pick 50 psi? I thought we could use 60 psi. Why did I pick 50 psi? In case there's a leak, okay, could be. You're using air, right? So can I guarantee I always have 60 psi? No. So that was a choice I made. You could choose to use 60 psi. And based on, I went to Clipper to use their sizing tool and came up with a minimum 2-inch size. Can I use bigger? Sure. Now, I actually are going to use 2 cylinders. So what size cylinder did I buy? Did I buy 1-inch cylinders? Is area proportional to the radius? No. Yeah, so it's an R squared term, right? So you have to be careful. You can't just assume that I can divide by 2 if I want to do the same work with 2 cylinders versus 1, that I could just have the size of the cylinder. It won't work. I think I had to go like 1.25 inches or something like that. So you don't save as much as you think you're going to save. So some watchouts, again, applying force at an angle, push versus sort of friction, and reaching top dead center. Who knows what top dead center is? I know these guys. Do you guys know what top dead center is? Does anybody know? Do you know what it is?
Bottom dead center, but they used it in video.
Well, top dead center is up here, bottom dead center is down here.
Well, that's the bottom, but
I don't know. So,
timing might
so remember on the robot I showed you that cylinder was not perpendicular to the force that I was applying, right? So in a car engine, right, you've got top dead center, and if you're pushing a rotary, we should just get. All right. So now I attach a cylinder here. Rotate that disc, right? When I get to a point where this is in line, my force is in line with the direction I'm pushing, I reach a point where I can't push anymore. It's because it's top dead center.
Yeah.
Right? So you have to be careful of when you're doing things at an angle that you don't get yourself into a position where there's no force applied anymore to it. And I don't think I drew that correctly.
Or is it where you can't return it because you're...
Well, yeah, right. So I know if I do it like this,
It's like through the axis, you know?
yeah, definitely if I do it like this, right?
Yeah.
Now I'm top dead center. Now when I try to retract, what happens? I'm just pulling straight through this center, and it will not move either way. And by the way, that applies to whether or not it's pneumatic or it's electric. So remember that little shifter I had over there to send that rod out? That's the problem I had on that. That was not an easy design, let me tell you. Because I would get the top dead center and that thing would just lock up and I'd be done. So it's real, it happens. And when you're not paying attention, it'll jump up and bite you. All right, so you guys get a chance to do the sizing exercise. Here's the requirements. I want to extend the gripper arm 36 inches. The gripper weighs 20 pounds. Your task, calculate the bore size. And list other requirements and assumptions, if any. Okay, go. Need a pencil? What's that? We talked about it earlier with the calculation. It's already in your email. Go back to the cylinder. Somewhere we talked, well, in fact, somewhere it's in here. What's PSI? Remember that discussion about PSI? What's that? But they had no idea. Got an answer? Who's got an answer? I mean, even with the calculators today, you can't. It's only one calculation.
It's a 3/4 of an inch.
3/4?
Way less than that.
Really?
Is it conservative?
Conservative, okay.
I mean, the math.
So I cheat. I just went to Clippard, and they have these things called calculators. Now, the other calculators are kind of worthless because all they are is conversion, unit converters. But the bore calculator actually does work. So I put in 20 pounds. You didn't ask me the one question. What's the pressure? What pressure did you guys assume?
Assume 50.
You assumed 50?
Make the math.
Used 40? There you go. There's nothing wrong with that.
That does make it easier.
So they recommend 7/8 of an inch bore size. Now they've got a 50% safety margin in here too. I go
Well,
to,
what's the rod size?
doesn't say. But you can say push or pull, recalculate, still says 7/8.
We have TV say slow.
7/8.
Still 7/8. What's that tell you?
7/8.
It's probably what they sell.
7/8 is oversized a little bit for medium, or for slow. Probably just about right for medium, right?
Do they sell a 36-inch that's
And if you go all the way up to fast, 80% safety margin, inch and a 16.
So,
That's a lot of safety margin.
so when we use pounds per square inch, we're not taking into account friction.
That's right, you're not.
That's the safety margin.
That's the safety margin. But you did put some safety margin there because you picked 50 PSI. So that's accounting for some of it. What if I make this 60? See what it says if I put 60. Look at that. So before, at 50 PSI and 80% safety margin, the bore size is 1 to the 16. Now it's down to 7/8 of it. With 60 PSI. 10 PSI makes that much difference.
What's the safety margin we use actually?
It is, you're oversizing, how much you're oversizing the cylinder to deliver the force that you need. So you have things in the system that you have control over, like the friction in the system. Right? So by oversizing it, so you're actually being able to apply more force than what you actually need. That's what the safety margin is. If I go to medium at 60 PSI, still 7/8, slow, down to 3/4. So what that means is that there's a chance that, that cylinder won't extend as fast as you want if you went to the least conservative 20% number at 3/4 inch.
Okay. What's the
I'm not
difference?
super in favor of this calculator, but it's quick and easy. And it just illustrates that there's a lot of judgment that you have to use in terms of sizing the cylinder. It's not precise science.
Now the link below that is stainless steel.
All of Clippard cylinders are stainless steel.
And how much does that cost?
What?
A 6-inch bore, 50 PSI, 6-inch stroke.
36-inch stroke? Well,
Whatever, 3/4 inch bore, 36 inch.
I don't know, actually. I don't know if he'll give us a cost or not.
Give me the rules, just give me a ballpark. Pick any one.
You must enable cookies to use the online store. Okay.
Sorry, I asked.
I'm not.
Don't open that. No.
I'm not sorry yet.
You're at the right.
Right.
Here?
All the way up to the upper right.
There's a little search box.
I'm in search right now. I'm in settings right now.
Go to the
Go to the
right.
right, there's a search
Type in
box.
cookies. No,
Just type in cookies here.
type cookies in there. There. Seconds.
Okay. Yep. Content settings, this one? How about this? Well, it says I can allow, it says allow local data recommended. What's that? This one? It says historic cookie. I have to restart. All right, now it's just getting.
Like I said, sorry.
All right. Oh, that's nice. Okay. Anyways, that gives you a flavor of what you need to do to size the cylinder. And as I said, other like Bimba, they have a sizing calculator, and it's actually a little better, I think. Than
What was that?
Clipper's. This was Clipper's,
Right.
but Bimba is, as the last, as long as I can remember, offered three cylinders to the FRC team, and you get within a limited selection, you get to pick what cylinders you want.
Oh.
So,
That's BIM.
BIMBA. BIMBA. All right, let's move on. I'm sorry it's taking so long. I didn't realize. Was this scheduled for only 2 hours, or was it 3?
Scheduled till 3 o'clock.
Gosh, I'm gonna have to change this presentation because this is. Did you guys fill out an evaluation form? Okay, great. Thanks for coming. And again, if you have any questions, please feel free to email Lakota Robotics, and we'll answer questions, or set up a time you can come back and we can talk about it. So, okay? You're welcome. So, air consumption is an interesting topic. It's also very difficult. If you want to do the calculations manually, it's rather tedious. You know, what we really want to know, we don't really care how much air consumption we have. What we really care about is how often will the compressor run, because that's what's draining the battery, right?
Could you like in a car, they have the vacuum sensor, and you mash it down on the gas, the air conditioner, compressor shuts off. And you let off the gas, and then the air compressor, you could do that with the
You can do that.
C-radio and say, hey, they're really moving. When they slow down, they'll be shooting, but while they're moving, they're not shooting. I will manage the...
Right, unless you want to pre-charge and be ready so that when you get there, you can shoot right away instead of having to wait for the compressor to charge the system.
But as you're turning around and back to the feeder thing, you can charge it. Anyway.
Yes, that's all things that you can do to manage.
People have thought of, yeah.
Right. To do the calculations, what you're going to need is all of this stuff. And the hard part is not what actuators you have, not the amount of storage. Temperature and pressure, you just pretty much decide you're going to run at 60 psi or 50 psi and ambient temperature 70 degrees. That's close enough. That's easy. Leakage rate, just assume you don't have any. And don't worry about this to start with, just as a start. This is the thing that you're not going to know. number of cycles for each of those actuators and the time between those cycles. Because every game is a little bit different, it's right, you're not sure how that, depending on what somebody's doing with you for the game. You can maybe do end game, like you're hanging the pyramid, you're gonna know that, but you're not gonna know how much you've used up until that point. So it's tough. You have to make some estimates. And here are the equations. I'm not gonna go through the equations, I give them to you. You can look at them on your own. There's a rule of thumb that I found last year. It says set your air receiver size in gallons to compressor capacity in CFM. This year I found a website that said, well, the rule of thumb used to be 1 gallon for every CFM of compressor capacity. It's up to 3, but those rules don't apply anymore. So they didn't say why. What's the problem with the rule of thumb? It's all approximate. Everybody's thumb is different. You don't know what assumptions were put in to generate what that rule of thumb is. They tell you that, and it's not a rule of thumb anymore. So here's a simple example. You've got 2 1.5-inch bore cylinders. You get the FRC minimum requirements, so you're running at basically 50-60 psi. You got 1 3/4-inch bore, 36-inch stroke cylinder, ambient temperature. How many reservoirs should you put on the robot? Well, if you go back to here and you think about all of this stuff, it'll take you a while. What's the game? You know, how often are you going to make a trip up and down? All that stuff. What I did is I used the rule of thumb. I said, okay, I have a compressor with a 1.05 CFM rating. How many air receivers does that mean? All right. I did the calculation. It comes out to 8 tanks.
4 liters.
Right? 8 tanks. So how many tanks did we have on our robot this year? 2013. 8! Son of a gun! But I would start out with, 2, 4, 8, depending on how many cylinders you have. The less cylinders you have, the less tanks you're going to need, right? Because you're going to have less consumption. But if you have big cylinders, but they're really big, they're going to use a lot of air. So, you can do some quasi-estimating by just looking at the volumes of the cylinders versus the volume of the air tanks, right? Assuming the PSI is the same. So if I have a cylinder that takes up, 500 ml, one air tank, every time it runs, that means that the compressor is going to run every time that you extend that cylinder, right? So you could do some guesstimates just based on that. And then what I would do is do your guesstimates and do it early. Run your robot and see how often the compressor comes on and see if that's acceptable or if it's running all the time. And make sure your code's right, sir.
So, I guess you could think about having tanks as sort of on reserve, like with a final push or something like that.
Right.
And then you charge them all at the same time.
What's that?
You can charge all the tanks at the same time. You can't just charge a few of them.
Right. Oh, is that one of the rules?
Well, no, it's just the way it has to work.
Well, otherwise you'd need
Yeah.
4 gauges, 4 pressure.
Right. But what if? Let's suppose you wanted to reserve 2 tanks for the hanging.
Okay, so let's go back. Let's go back here. Okay, so this is a typical system, right? Normally my tanks are on my high pressure side. Why is that? This is 120 psi up to this regulator, which
You
is,
want to pressurize it with the.
they hold more air, right?
Right.
Right? But to do what you wanted to do, right? Why couldn't I have a pressure regulator? So let me sketch this over. So what you're suggesting, right, if I'm correct, So let me draw it up until the point of, so here's my compressor, my relief valve, okay, my pressure gauge, okay, what else I need? I need my dump valve, okay, so that's all that good stuff now, right? I don't have any tanks yet. So what you're suggesting is I put a tank here and a regulator, right, that goes to solenoid valve to one cylinder, right? And then if I put another receiver down here, right? That's what you want to do?
With the check valve.
Right, check valve. So you want to put a check valve in here?
Right.
Well, that actually might work. Oops, I drew them backwards. What pressure are you going to set that check valve at?
Check valve plus pressure. It's just in one direction.
Do you set
Well, but
pressure?
there's usually a spring in here that sets. Let's see.
It just says don't go this way.
Right.
Go that way.
Right.
And the only thing it did have to run out of gas. Or you didn't use up all the gas.
You don't have it for the other. Right.
How would you
Put
charge?
another check valve. Because I was the wrong side. Say this is the higher priority. If I have to let
Or you can have computer actuated valves, obviously.
Well, these are computer actuated, right?
Yeah. So you could do that.
But
Except now you're putting 120 side. It's code.
one thing is you cannot put solenoid valves on the high pressure side. See, these are 60 psi regulators, right?
Okay.
So this is 120 psi side, and this is my 60 psi side.
Yeah. So all you could have is that check. Can you have the check valve on the high pressure side?
You know, I don't know. I don't know why. Well, you might not be able to. You have to read the rules more closely to see. Actually, I think on the high pressure side, the only thing that you're allowed, I don't think you're allowed these. The only thing you're allowed are these things.
So that's why you have to have a multi.
Yeah.
Because if you drain one, then it'll flow right back right into the other.
Right.
Okay. So that's key here is that what you're saying is you can only have the gauge, relief valve,
Let's look at the
compressor
rules
on
real
the high
quick.
pressure tank, right? On the
I
high
got the
pressure
rules.
side.
I got the rules called up here somewhere. Pneumatic system. So here's the rule. All pneumatic components, 125 psi. Two may be cut. So this is an old drawing. It's I don't hold you to this exact configuration. This is so old, they're still showing the steel air tanks. So here, compressed air on the room is supplied by one and only one compressor.
compressors can recharge a compressed air tank only on the robot.
Where'd you see that? Where you,
In the blue bottom half.
this right down on the robot, this part?
Right.
Where we left off the robot, used to recharge compressed air and storage tanks on the robot prior to bringing it on.
But it doesn't say, we left off the robot and used to pre-charge compressed air and storage tanks off the robot.
Right.
Or
Yeah.
just because it doesn't say on.
I don't think anyone's ever considered that, trying to do it that way. So this is a little ambivalent regarding that ambiguous regarding that technique. So I don't know.
So, here's a question. In general, if you have, you come up with these interpretations of the rules, is there a
Field technical
is there a governing body you can appeal
Yes.
to?
So the procedure is thus. And so during the build season, they publish the rules, and then they open up a Q&A, question and answer forum. So someone from any team, from the team, will post questions regarding interpretation of the rules.
Everybody gets to see that.
And everybody gets to see the answers.
There's no IP.
There's no IP there. Everybody gets to see the answers. And in fact, some answers, questions, will generate changes to the rules. So what happens is if the rule, for example, is obviously ambiguous, someone asks the question, can I do this? They may change the rule to make it unambiguous, one way or the other. So yeah, that's usually what generates changes to the rules is all the Q&As. There's 6 or 8 people on the game design committee. There are, most teams are 25 people, right? Okay, times 2,500. There's no way they can compete with that kind of brain power.
If everyone works together, they can find every loophole and exploit it.
Yes. You would have to ask the question.
Right.
Now they may say, well, because we cannot guarantee that you're only using the onboard compressor to pressurize the tank, I don't know, but they do this for a safety reason, right? They don't want anything. And last year, people were, like I said, were trying to use compressors for nail guns and that kind of stuff, pressurize a robot before the match. And in some venues, it was a real problem. They actually forced teams to take them out of the venue. There were some hard feelings about it, etc. Sure. That stuff happens. Huh?
I always have to keep the intent.
Keep the intent, right. Keep the intent. So, when you got 17 or 20, air tanks, you got or 20 air tanks and 17 minutes to recharge them, well, if you get to the finals, you only get 5 minutes, 6 minutes between matches. What are you going to do? You're toast. That compressor will be running continuously the whole match.
You need to swap out a charged air tank.
Hi. Okay, so let's see what else it says here. Must be number must be 1. So here's the other thing. All working air must be provided through one primary adjustable pressure regulator. So even having a tap, right, with 2 regulators, you can't do that. Right? One primary adjustable. So even if we did this, right? This is not legal. Because it says all working air must be provided through one primary adjustable. So I can't do this, right? I can do this.
Whichever one's lower.
Right. So this might be 60 and this is 40, but I cannot have two regulators connected to the stored pressure side.
There are a lot of ways to break the rules.
There's a lot of what?
There's a lot of ways to break the rules.
Yes.
But did you?
We had this. We had a 60 psi, and then off the 60 psi, we had a 40 psi regulator. So, and as long as this one is lower than this one, that works just fine.
Yeah, that would be the issue with
Right. And the rule of thumb, if I remember this correctly, is 10%, right? So if you want this one to be, so if you wanted this one to be 60 or 55 psi, this would not work. Right? This is 60. The low pressure side on this, so the high pressure side of the regulator should be 10% higher than the output pressure. So that if this 10% of this is like 6 psi, right? So that's only, that'd be right. So that's the rule of thumb. And usually if you're this close together anyways, you would just use a 60 psi side. I have a hard time believing that would make a difference. Yeah.
All right, that's fine. So
all the rules are out there. Here you go. Only the compressor, relief valve, pressure switch, pressure vent plug valve, pressure gauge, storage tanks, tubing, and connecting things may be in the high pressure pneumatics or the upstream from regulator. So there you go. That precludes you from using those. So there's two rules there precluding you from doing that because you're trying to do. One, you can't plug the check valve in there. Two, you only have one regulator. Keep the high pressure.
I guess the first thing you do is remove the
fine tune.
only have tubing, but you can make your own valve with solenoid and the tubing.
It actually specifically says no. Somewhere earlier on. Okay. The only pneumatic items permitted on the robot, including items listed below. I know it says it somewhere, but the problem is if you make it yourself, how are you going to guarantee that it has a working pressure of 125 psi?
So we're looking there.
Well, I'll tell you. Well, you could accidentally do that in somewhere in your robot to restrict the airflow.
Right, so we're going to keep those two cylinders in fans.
I did inspection years ago, and they had the same rule about you can only use commercially off-the-shelf parts. And some 14 had made their own flow control valve. They had taken a small block of aluminum, drilled it out, got a little brass needle valve, and put it in there and created their own. And they said, "I'm sorry, but you have to take those off. They're not legal." I said, "Well, I mean, we just went to the this was a championship. We're at such and such regional, they said everything was fine." I said, "Well, look," I said, "not everybody is an expert on pneumatics. It's something that a lot of engineers don't have any, and they may not recognize that it's not a legal part. Unfortunately, I do know that it's not a legal part, and I cannot pass it." He said, "But our robot will beat itself to death." I said, "I know. I know exactly what the flow control's do. And it limits how fast that cylinder can move." And I honestly don't know what to tell you to do other than see if you can get some flow control if you don't want something illegal. And we can deal with it. But that, that's one of the reasons I don't do inspections anymore, because sometimes you get into situations that are just heartbreaking, right?
I thought, first thing I said is you're just going to get some schedule A and tank.
No,
You're using these little ones. Fit the space you want.
Okay. Any more questions? Where are we? So there's your sizing. So there's your information. So did I cover everything that you guys questioned? I didn't ever answer what the C-RIO was.
Yeah.
The C-RIO is the computer
Okay.
that controls the robot. So it's a National Instruments industrial quality computer. It has a FPGA on it, which I can't remember exactly what it is, gate array, something. Gate array.
Field program.
There you go, thank you. That stores your program on.
Okay.
Okay.
Call.
Yes.
Our email for the team is 1038.
1038 at LakotaRobotics.com. At LakotaRobotics.com. And we have some flyers back by Jimmy's desk sitting on the floor if you want to go grab them.
She's a visitor from Walnut Hills.
Oh, okay, great.
Yeah.
Yeah, they used to have a. You guys used to have a team. You guys used to have a team. Anyways, so you can go over here and see them on our robots, and they have slots. So it's a slot-based system where you plug in cards. So minimum you have to have is a digital card in there, digital I/O card, and an analog I/O card in there. And the standard today is a 4-slot. Originally when we started, they were 10-slot, so they took up a lot of space. We have both versions.
Sir, do you have a class on electronics?
Okay, so I do have, and talk about demos, if you want to spend the time, I have all the parts. We have to put in a couple of fittings and put things together. Oh, one thing I forgot to mention that you need that's a minimum requirement that they don't talk about. Teflon tape. Okay? If you do not use Teflon tape, your fittings will leak.
Even if you do use Teflon.
Sometimes they still leak, yeah. And some of these still leak. So I have the tubing and I have all the parts if you guys want to come up and we can actually assemble it. I actually have a computer to turn the compressor on and off and to cycle the solenoid valve. Do you guys want to do that? Or you guys? I know we ran way late.
I think we used up so much of your time, and we got what we needed.
Well, like I said, you're more than welcome to come back at a later date. We can sit down and we can go through the whole process of hooking everything up.
It's awesome. Yeah,
I'd be glad to do that. So
I think we're good.
I will.
They ever use hydraulics?
You're not allowed to use hydraulics.
Okay.
That is prohibited.